A microservice crashed every 10 minutes with OOM-Killed. Heap dumps showed 80% of memory consumed by a single hash map holding denormalized order data. The team assumed a memory leak, but the real culprit was loading all 2 million rows from a denormalized table on startup. Let's break down why denormalization without limits is a memory bomb. Welcome to TheCodeForge. Before we dig into that production issue, let's cover normalization versus denormalization. Normalization organizes data into separate tables to reduce redundancy and ensure consistency. Denormalization intentionally adds redundancy by merging tables or duplicating data to speed up reads. The cost is that writes become more complex. As a rule, always start with a normalized schema and only denormalize when you have a measured read bottleneck. Before normalization, databases were a mess of duplicated data. Updating a customer's address in one place left it wrong everywhere else. That's an update anomaly. Normalization splits data into tables so each fact lives exactly once. The cost? You need joins to read related data, but the benefit is huge. No contradictory data, no wasted space, and simpler updates. Here's a normalized schema for customers and orders. Each fact is stored once. Customer details in the customer's table, order details in the order's table. To read related data, you join on the foreign key. This ensures consistency. If a customer changes their name, you update only one row. Denormalization shines when you have a read-heavy workload with a fixed set of queries. For example, an e-commerce product page that shows product name, category, and average rating. With denormalization, you store all that in one row. Reads become a single index lookup, but writes get more expensive. Updating a rating now requires updating every product row that references it. Here's a denormalized product table. The read query is simple and fast, no joins. But notice the write. If the category name changes, you must update every product row in that category. This can be slow on large tables. Never denormalize a value that changes frequently across many rows. You don't have to choose one extreme. The battle-tested pattern is normalize your write model and denormalize your read model. In PostgreSQL, use materialized views. In MySQL, use summary tables updated via triggers or scheduled jobs. This gives you data integrity on writes and fast reads at the cost of eventual consistency. Here's a materialized view that pre-joins orders and customers. The view is refreshed periodically, so reads are fast and don't need joins. The normalized tables remain the source of truth. This pattern is ideal for reporting queries. Every denormalized column that's derived from other data multiplies your write cost. For example, storing customer name directly in the orders table means that when a customer changes their name, you must update every order they ever placed. This causes full table scans and lock contention, leading to deadlocks and timeouts. This is a bad design. The customer name is denormalized in the orders table. When the customer changes their name, you must update every order row for that customer, locking them all. This blocks other writes and can cause deadlocks. The better approach is to keep the write path normalized. Store only the customer ID in orders. For reads, join with the customer's table and cache the result in RIDIs. This avoids write amplification and keeps updates fast. Normalized schemas rely heavily on indexes to make joins fast. Always index foreign keys and columns used in where clauses. For denormalized schemas, you need fewer joins but wider indexes. Consider covering indexes. A common mistake is denormalizing without adding an index on the denormalized column, then wondering why queries are slow. Here's how to index properly. For normalized schemas, index foreign keys like customer ID. For denormalized schemas, index columns used in where clauses like category name. Always use explain analyze to verify your indexes are being used. Some data doesn't need normalization. Logs, time series metrics, and event streams are write once, read many with no updates. Normalizing them adds join overhead for no benefit. Use a wide table with all fields denormalized. In NoSQL databases like MongoDB, denormalization is the default, but be careful with document size limits. For immutable data like logs, a denormalized table is perfect. No updates, only inserts and reads. The username is duplicated, but since it rarely changes, the cost is negligible. Queries are fast with a single table scan. Before denormalizing, ask, can I cache the query result? A Redis cache with a 5-minute TTL can absorb 99% of read traffic without any schema change. Denormalization is a permanent schema change that complicates writes. Caching is temporary and reversible. Only denormalize when caching isn't enough. Here's a cache-aside pattern. The application first checks Redis. If not found, it runs the normalized query with a join, then stores the result in cache with a TTL. This avoids denormalization while still providing fast reads. This is the same issue we highlighted at the start. Here's exactly why that happened. The service loaded all orders into memory from a denormalized table on startup. The table had 2 million rows, each with duplicated customer names and item descriptions. The HashMap grew to 3.2 GB, exceeding the 4 GB container limit, causing OOM-Killed every 10 minutes. The fix was to change the query to load only the last 30 days of orders, about 200K rows, and normalize the schema. Memory dropped to 400 MB. They also added pagination for the rare full-scan reports. The key lesson: always set a time or count bound on in-memory denormalized data. Loading all denormalized data into memory on startup is a common mistake. Without a retention policy, the data grows until it consumes all available memory. Always limit the data loaded to a recent time window or a reasonable count. Do not update denormalized columns synchronously in the same transaction as the source update. This doubles your lock time and risk of deadlock. Always use async propagation like a queue or CDC. If you denormalize a column like category name that changes often, updating it requires scanning and locking many rows. I've seen a category name update take 30 minutes on a 10 million row table, blocking all reads. Always keep frequently updated columns normalized. The article mentions data inconsistency between denormalized copies, but doesn't show a concrete reconciliation query. Here's a SQL snippet to find discrepancies between a denormalized column and its source. The article advises against synchronous updates for denormalized columns. Here's a pattern using a message queue, e.g., RabbitMQ, to propagate changes asynchronously, reducing lock contention. The article uses PostgreSQL's Materialized view syntax. MySQL does not support materialized views natively. You must use summary tables with triggers or scheduled events. This is a critical distinction for MySQL users. Here's how to diagnose and fix common issues. For slow queries, use Explain Analyze to identify full table scans and add missing indexes. For data mismatches, run a reconciliation query to find discrepancies. For memory issues, check the size of denormalized data in memory and add limits. Let's run through some common interview questions. How does denormalization affect write throughput under concurrent load? It increases lock contention and deadlock probability because updating one fact may require updating multiple rows. When would you choose denormalization over adding a cache layer? When the query is too complex to cache efficiently or the dataset is too large for cache memory. What happens when you denormalize a frequently updated column? Write amplification, high lock contention, deadlocks. Mitigate by keeping the column normalized and using async propagation. And a few frequently asked questions. What is normalization? Organizing data into separate tables to reduce redundancy and improve integrity. What is the difference between normalization and denormalization? Normalization reduces redundancy. Denormalization adds redundancy for read performance. How do I decide when to denormalize? Start normalized. If reads are slow, try indexes and caching first. Denormalize only for hot, stable read paths. To recap, always start with a normalized schema. Denormalize only when you have a measured read bottleneck that caching can't solve. Remember that denormalization increases write cost and complexity. Use materialized views or CQRS to get normalized writes and denormalized reads. And always fix indexing before reaching for denormalization. Ready to go deeper? Up next, ACID versus base, then change data capture, CDC, then database federation. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.